Today's going to be 60-2, and we're going to take a look at graphs of polynomials. So today we're going to sketch a polynomial and understand and use the intermediate value theorem. Now when we sketch a polynomial, we're going to be using these three different things here. So the three pieces of information that we need are going to be the zeros and its respective multiplicity. Now we haven't really talked about what multiplicity is yet. We're going to talk about that very shortly. We need to know the y-intercept. Now remember, with the y-intercept, this is where we're going to plug in 0 for x, and then we need to know what the end behavior is. Now an extra piece of information that may be helpful is going to find the intervals in which my function is going to be positive and negative. That basically just tells me what's above the x-axis and what's below the x-axis, but it's not necessary. So let's talk about that multiplicity that I had originally mentioned. So what is multiplicity? It's essentially the number of times the zero occurs. So in this example here, this is my polynomial. My 0 here, if I set this equal to 0, this equal to 0, this equal to 0, and this equal to 0, my zeros are going to be positive 2, negative 5, negative 1, and positive 1. Now my multiplicity, we're saying that the multiplicity is the number of times the 0 occurs. So because this says x minus 2 squared, I have 2 of these. So my multiplicity for this 0 is 2. I have 4 of these, so my multiplicity for this 0 is 4. I have only 1 of these, so my multiplicity for this 0 is 1. And I only have 1 of these, and so my multiplicity for this one is 1. So that's the multiplicity. So now we're going to ask the question, why do I need to know the multiplicity? Now the role of multiplicity is essentially how the graph interacts with the zeros. So the multiplicity essentially provides us information about how the graph interacts with the zeros. So if I have a polynomial and I say that my 0 has a multiplicity of m, I just want to know if my multiplicity is even or if my multiplicity is odd. Because if my multiplicity is even, what I can then say is that my function touches and rebounds, or another phrasing that's used, it bounces from the x-axis at that 0. And now if m is odd, the graph is going to cross through that x-axis. So I need to know if my multiplicity is even or odd because my graph will interact it. Now what I mean is, let's say if this is my 0, and I have my polynomial, if my multiplicity was even, it would touch it and bounce and go in the other direction. If this was my 0 and this is my polynomial, if it crossed through it, that means that I know that my multiplicity was odd. So let's look at another example here. I know that my zeros, I have them listed there. My zeros, if I set equal to 0 and equal to 0 equal to 0, my zeros in this case are 2 and negative 1. Now I don't repeat it, right? I don't write 2, 2, 2. I only have 1 0, but this is where labeling the multiplicity comes into play. How many of these 2's do I have? I have 3 of them, so I'm going to say my multiplicity is 3. I only have 1 of these, so I'm going to say my multiplicity is going to be 1. Now remember, we said that if our multiplicity is odd, that means that the graph will cross through the 0. So let's take a look at a picture of that. Notice my multiplicity is odd, the graph crossed through it. It's odd here, my graph crossed through it. Now you're probably wondering, you're like, wait a minute. The way that it's crossing this graph is different than the way that it's crossing this graph. Now I am going to mention the fact that the way that it's crossing, it is different for a reason. And essentially, when your multiplicity, it's odd, we know it's going to cross through, but if it's 3 or higher, it's going to cross the graph at what we call an inflection point. And that creates this like new swivel. Now, we're not going to spend a whole lot of time discussing that. All I need you to do is just draw that it crosses through. Now, when you get into calculus and you understand what inflection points are and concavity and how all that is going to interact, then what you need to do is you will probably have to focus more on drawing your inflection point correctly. But for now, as long as you remember multiplicity is odd, it's going to cross through. Let's take a look at another one. My zeros, 1, 1, -2, and -2. So I only have 2 of these, so my multiplicity is 2. I only have 2 of these, so my multiplicity is 2. So let's look at a picture of that. Now if you also notice here, right, we said when the multiplicity is even, it's going to bounce. So it hits the 0 and it goes back down the other direction. Goes and it hits the 0 and it goes back down in the other direction, right? It's almost as it bounces at the 0, like a ball would bounce at the floor and go back up. But in this case it's down, so it's going to go back down. So let's actually sketch a couple polynomials. So remember, I said we need to know these 3 pieces of information here. So the first thing it says is we need to state the zeros and the multiplicity. So that means I have to set each of these equal to 0. Now when I do that, I'm going to get x equals 1/2 and x equals -1. Now I only have 1 of these, so my multiplicity is going to be 1. I have 2 of these, so my multiplicity is going to be 2. Now remember, when my multiplicity is odd, it's going to cross. When my multiplicity is even, it's going to bounce. Now my y-intercept. This is when I have to plug in 0 for x. So I'm going to get -3 times 2 times 0 minus 1. 0 plus 1. So I'm going to get -3 times -1 times 1 squared. So that's going to give me 3. So my point is going to be 0, 3. And now my in behavior. Well, for the in behavior, we have to look at the leading coefficient. So I have to multiply all of the leading coefficients here. So that's going to give me -3 times, I have this one, so 2x, times I have this one squared, so x squared. And so my a sub n x to the n power, that's going to be -6 x to the third. So now my a sub n, I know it's going to be negative. My degree, that's going to be odd. So when my leading coefficient is negative and my degree is odd, it's going to go like that. That's what my in behavior is going to look like. So now that I have all this information, let's sketch it. So here's my graph here, and we said that my in behavior should have this type of image. So I know it's going to go up there, and then it's going to end up going down there. There's something that's going to happen in the middle. We said that my zeros, those zeros are going to be at -1 and at 1/2. So now drawing these, right, my graph is going to start from the in behavior, so it's going to come down from the in behavior. Now it's going to get to this -1. Now at the -1, we said the multiplicity is 2, so that means it's going to bounce at the 0. Okay, so it's going to bounce, and it's going to go up to the y-intercept. So kind of like drawing this again, just to make it a little bit neater. It's going to come down, it's going to bounce, it's going to go up to the y-intercept, and then it wants to go next to the next 0, and the next 0 at 1/2, it's going to cross. So it's going to go, it's going to cross, and it's going to go down forever there. Now, I'm going to be honest with you, that is not an ultra accurate sketch. Right? Other things could happen in between this. This could have technically gone up and then maybe crossed down that way. You know, it could have gone up here and then got back down. We don't know those things. Now, the reason why we don't know those things is because the number of tools that we have to accurately describe or draw this graph, it's not sufficient enough. But what we have drawn is sufficient enough. It passes through the zeros, it interacted with the correct multiplicities, it passed through the y-intercept, and it follows our in behavior. So because it followed those 3 major things, that is a good enough sketch of what our polynomial could look like. Now, we could always, to make it more accurate, we can plug in values for x. I could plug in -1. I could plug in -2. I could plug in, -0.5. I can start plugging in all of these values for x to get that more accurate description. Let's look at another one. So the first thing, state my zeros. So my zeros are going to be -3 and -1. Now I have two of these and I have two of these, so my multiplicity is going to be 2. My multiplicity is going to be 2, which means they're going to bounce. My y-intercept, right? We said we need to plug in 0 for x. So that's going to be 2 times 0 plus 3 squared, 0 plus 1 squared. And so that's going to give me a whopping 18. So my y-intercept is going to be 0, 18. And last, my in behavior, I need to know what my leading coefficient is. So 2 times, this will be x squared, times, that'll be x squared. So I'm going to get 2x to the 4th. So that means that my leading coefficient, I know that's going to be positive. My degree, that's going to be even. So then drawing this, my zeros, I have -3 and -1. My y-intercept, I'm just going to say that that's 18, just to save time. And then my in behavior, we said because of my in behavior it should do something like that. So it's going to come from up here and it's going to go up there forever. Okay, so now drawing our polynomial. So it'll come here, it's going to bounce, and then it's going to come straight up. Now it's a little wobbly, I know, not super accurate, but at least it has the generic image of what it could potentially look like. Probably would have been better if this was just a little bit more angled correctly there. But that's essentially the image. It follows the in behavior. It crosses through the y-intercept. It passes through those zeros and bounces at them. So this is an accurate enough sketch of our polynomial. Now the last thing we're going to talk about is the intermediate value theorem. This states that if you have a continuous interval, and remember all polynomials that we've talked about so far are continuous, containing two x values, a and b, and we're going to say that it's in order, so a comes first and then b comes second. If f of a and f of b have different signs, meaning, like my one y value is positive and one y value is negative, or one y value is negative and the other one is positive, then we can make the assumption that there's at least one zero between those two x values, a and b. So there's at least one zero. And let's visualize it. I mean, if I were to even draw this out, there's my x-axis. If I have some a and b, this would be f of a, and let's say this is f of b. So I have this value here and this value down here. Well, to connect them, if it's continuous, so they are connected, well, it has to cross the x-axis at least once. So that's all it's saying, is if the signs change, we can make the assumption there's at least one zero. Now there's a couple of assumptions that we tend to make that can be a little deceiving about the intermediate value theorem. The first is that the intermediate value theorem cannot be used to determine whether there is a real zero between them. So in this example here, if you notice, my f of a is positive, my f of b is positive. But along this interval, it crossed the x-axis here and here. Well, there's two zeros between there. So if it fails this test that we're doing, you cannot make the conclusion there is no zero. You just can't assume that there is one. The second assumption that tends to be bad is that sometimes when we do our intermediate value theorem, our f of a is positive, our f of b is negative, so it changes sign, we assume that there is only one. you can only assume that there's at least one. And here's the example there, because if it crosses 1, 2, 3, 4, 5, 6, 7 times, there's actually 7 zeros between those two values. So we're going to eventually use and find more accurate means to locate and find those zeros. But just know that with the intermediate value theorem, it cannot be used to say that there is no zero between it, and it cannot be used to determine if there are actually multiple zeros in between them. The only assumption that you can make is that there's only at least one zero. In this example here, it says use the intermediate value theorem to determine whether the function has at least one real zero between a and b. So if my interval a is -4 and my b is -2, that means I have to plug in -4 and I have to plug in -2. Well, notice my y value is -24 and 8. They change signs. So according to the intermediate value theorem, I can make the assumption that at least one zero exists between a and b. There could be more, I don't know, but I can at least make the assumption that there's at least one. For this next example, in this interval -1 and 3, when I plug them in, they're both positive. Now, there could be a zero in between them. I don't know that. I can't make an assumption that there is one, though. So I would have to do other things to determine if there is or not. So this does conclude our lesson. If you have any other questions, please leave them in the comments.